Welcome to Applied Bioinformatics. In this video, I want to show you some code that implements multiple sequence alignment. We extend the basic Levenshtein algorithm, and the key idea is that instead of processing two strings, we process two lists of strings. And these two lists of strings represent multiple sequence alignments that we align with each other. And this way, we can implement progressive alignment. A lot of the code will look very similar to the existing Levenshtein code, and the key difference is only where we move from string to list of string. So let's take a look. First of all, we've got a compare method, and this simply takes A and B, two characters, really characters in this case, and if they're identical and they're not, and A is not a gap, then the score is 0. If both are gaps, the score is 1, and otherwise it's 1.5. Now, sum of pairs is one of the important methods. Again, it's not really complex, but it's important because we have to change from comparing two single characters, as we did in the CMP compare method, to comparing lists of characters. And we do so by simply breaking down one list and the other list into the combination of all individual characters that are in both lists. And essentially sum of pairs implements what the name suggests. It's a sum of pairs. So C, which is the sum of pairs, is set to 0 in the beginning. We go through all of the characters in the first list A. We go through all characters in the second list B. We calculate their comparison value, add it to C, and return the sum. Then we have a function mindir, which you know already from previous videos. So this returns the minimum of the three numbers, A, B, and C, as well as the direction from where they were coming. Next we have the align method, and align takes as input two alignments A and B, the distance metrics d dir with a direction, and the position ij in which we are. So if I and j are both 0, that means we have the base case, we have the top left corner of the matrix, then we return this cryptic string. Well, it's not really that cryptic. So we have here a list consisting out of two pieces, and they in turn consist out of empty string here, and the times laying A means that m times we will repeat these bits. Yeah, so we create a list that has m times the list with an empty string in it. And it continues with n times a list with empty strings. So overall, we've got a list with m plus n times a list with an empty string in it. So otherwise, if we're not in the top left cell, we're going to check for the direction. So we are at ij and we were coming from north. So we continue the alignment. We keep those two alignments A and B. D dir doesn't change, but as we're going north, we change those indices I, and instead of j, it's j minus 1. And the result are two alignments A2 and B2. And now we have to combine them. In B, we will have the characters as they were generated for the alignment part of B. And this may not only be characters, it can also be gaps. But we don't really want to inspect that, because we know that for A, we have created a gap. Now a gap in this case is not a single dash, single character, but is rather a list of dashes. And that's what we have here. So what we're saying is we throw these two, A2 and B2, together in a list in which we take A2, which is an alignment, that means a list of strings, and we add to this list of strings gaps. So each of the strings is extended by a dash. And for B2, we're extending it by the characters as they were in the alignment B at position J-1. Yeah, and overall it's a list. So this is a list of string, that is a list of strings. So altogether we have a long list of strings. Something corresponding happens if we're coming from west. So only instead of J-1, it's I-1. And instead of putting a gap into A, we're putting the gap into B. And we're using the characters here as we use the characters there. If the direction was northwest, we reduce to I-1, J-1, and no gaps this time, but the characters from A at position I-1 and the characters from B at position J-1. So we saw here the gap method, and this is what it does. It's a one-liner here. So get A at position I, takes a list of strings, which is A, and returns the characters that it finds in each of the strings at position I. So we return a list, and the list is created as follows. For every string S in the list of strings A, we return S at position I. Now let's look at the add method. Here we take a list of strings A and we have a list of n characters. So we create an empty list A2, and for I in the range of length A, so that means for all strings that we have in the list A, we append to the string AI the character AAS at position I. And this is all put into the list A2, and then A2 is returned. Ints AB gives us the penalty for inserting or deleting into the alignment. So it's essentially the length of A, the length of B times whatever the gap score was. Gap A creates that high dimensional gap, so it returns a list with m entries of a single dash. Next we have the Levenshtein calculation, and it is more or less the same as you got to know it. There's only one difference, which is popping up here. All of the top bit is exactly the same as you know it. So as we're going north, west, and northwest, we have to use the sum of pairs. And as the sum of pairs is not operating on characters, but it's rather operating on alignments, we have to use those methods get and gap in this place. Yeah, so we create the sum of pairs of the characters at position ij in the alignment A, and we calculate the score against all gaps in B, or in the second case gaps in A and the characters at position J-1 in the alignment B, or the characters at I-1 in A and the characters at J-1 in B. And that's it already. So we return here the score that we get, so that remains the value in the bottom right corner, and we return A1 here, and this is now an alignment. That means it's a list of strings. Next, we've got the main function, multiple sequence alignment list, which takes a list of sequence of strings as argument, and we're starting off with B, which takes the first of these strings, so A at position 0, creates a list out of it, and then we say for all of the remaining ones, so we go through the list of strings A from position 1 to the final one, len A, and we calculate the score with the Levenshtein function between the existing alignment B and the newly added string A at position I. So as we're starting on with a single string in the very beginning, and as we're picking the second string, we're really doing here the stuff as we know it. It's one string against another string. But upon the next iteration, it will not be one string against another one anymore, but the alignment that we have generated, B, will consist out of two strings, and we're picking up the third one. And that will consist of three, and we're picking up the fourth one. In the end, once we have processed all of the strings, we return the alignment. And here we're printing the result of the alignment. And let's press play and see what we get. So here you can see beautifully we had February, and so on. So the second month of the year in various different languages. And you can see beautifully how it aligns and how we can find conserved characters, FE, and then we see some difference. Sometimes there is a B or two B's, sometimes this B turned into a V. And then we have matches again. We have a fully conserved R, then about U, A, E, I, there are some differences, and then basically a little conservation here with 4 R's, but however in this string this is missing. So quite useful, and you can see that multiple sequence alignment in its simplest form is not really looking that much different than the basic algorithm for the Levenshtein distance as we got to know it. The only difference is that we're not processing individual strings anymore, but that we're rather processing a list of strings, and when we want to compare list of strings, we need the sum of pairs as the key ingredients to make this fly.